Assalamualaikum warahmatullahi wabarakatuh. My name is Dayang Rini Najwa binti Muhammad Huza and my friend Nurul Hamizah binti Ali. We are from CS249582. We are going to present some theorem from factor group and cyclic group.
Question 1, number 5. Theorem. A subgroup of a cyclic group is cyclic. To prove this theorem, let G be a cyclic group generated by A, which means every element in G has the power of A. Notation: G generated by A, where G consists of element A power of n, where n element in integer. Then let H be a subgroup of G. If H has element E, then H is generated by E is cyclic. If H not consists of only element of E, then A power of n element H for some integer n element in positive integer. Then let m be the smallest integer in positive integer such that A power of m element in H. We claim that C equal to A power of m generates H. That is, H has a generator A power of m equal to generator C. Next, we must show that every B element in H is the power of C. Since B element in H, B also element in G. We have B equal to A power of n for some n. Observation from number theory: if m is a positive integer and n is any integer, then there exist unique integers q and r such that n equal to m multiplied by q plus r, where r is between 0 and m, in accord with the division algorithm for integer. For example, given m equal to 4 and n equal to 35, we know that if we divide 35 by 4, 35 is equal to 4 times 8 with remainder 3. Then A power of n equal to A power of m cubed plus r equal to A power of m power of q multiplied with A power of r. If we multiply above equation on the left with the inverse of A power of m power of q, we get A power of r equal to A power of m power of negative q multiplied with A power of n. Now, since A power of n element in H, A power of m element in H, and H is a subgroup, both A power of m power of negative q and A power of n are in H. Thus, A power of n power of negative q multiplied with A power of n element in H, that is, A power of r element in H. Since m was the smallest positive integer such that A power of m element H and r is between 0 and m, we must have r equal to 0. Thus, n equal to mq and b equal to A power of n equal to A power of m power of q equal to c power of q. So b is the power of c.
Let's see the example for this theorem. Let G be a cyclic group of order 12 and AB is generator. Then the group of G consists of generator A, where the generated A power of 12 is equal to the identity. Then the divisors of 12 are 1, 2, 3, 4, 6, and 12, and the group of G has a subgroup of order 1, 2, 3, 4, 6, and 12, and the generators of these subgroups are: for the order 1, we have the identity. For the order 2, we have the generator of A power of 6. For the order 3, we have A power of 4. And we have the generator A power of 3 for order 4, A power of 2 for the order 6, and A power of 1 for the order of 12. Next, let's see the theorem in question 2 number 4. Let H be a subgroup of a group G, then left coset multiplication is well defined by the equation AH binary with BH is equal to AB times H if and only if H is a normal subgroup of G. Let's prove this theorem. Suppose that this rule of multiplication is well defined. We let A element in G. We want to show that AH equal to HA are the same set. There are two ways to represent the product AH times A inverse H. The first way is let A element in AH and A inverse element in A inverse H. Then AH times A inverse H is equal to, in a bracket, A times A inverse H. Here we will get the identity where we will get the H. On the other hand, let X element in AH. By choosing representative X element in AH and A inverse element in A inverse H, then we will have X binary with the A inverse H equal to the bracket X A inverse times H. Since the left coset multiplication is well defined, we must have X A inverse equal to H, where H is an element in the subgroup of H. Then, multiplying both sides of the right by A, we get X equal to HA. Since X element in AH, therefore, it proves that AH is a subset in HA. Due to our hypothesis that the left cosets of multiplication is well defined, we can say that the cosets are omitting left and right. Suppose we wish to compute the left cosets of AH binary with the left cosets of BH is equal to the left cosets that containing ABH. We let AH equal to CH and BH equal to DH if AH equal to CH, since A element in AH, so we can say that A also element in CH. Then, we let A equal to CH1, where H1 is an element in subgroup of H, and also if BH equal to DH, since B element in DH, so we also can say that B element in DH. Then, we let B equal to DH2, where H2 is an element of the subgroup H. So that we multiply AB, we will get CH1 times DH2. By using associative add here, we will have C times in the bracket H1D times with H2. Note that H is a normal subgroup of G, so H1D is an element in HD where it holds also as DH. By associative of binary operation of G, we are using H1D equals to DH3, for H3 is an element in. Then, we have AB equal to C times DH3 times H2. Again, we are using associative here, and we will get CD times H3H2. So, since CD times H3H2 is an element in ABH, therefore, CDH is in ABH. Thus, it shows that H is a normal subgroup of G, and the left coset of multiplication is well defined.
Now, let's see an example for this theorem. Let G be an integer modulo 6 and H consists of element 0, 3. The cosets are 0 plus H consists of element 0 and 3, 1 plus H consists of element 1 and 4, 2 plus H consists of element 2 and 5. Below is the group table for integer modulo 6 with the heads at the top and left sorted by coset 0 and 3. If x1 and x2 are in the same coset and y1 and y2 are in the same coset, then x1 plus y1 and x2 plus y2 are in the same coset. We can define addition among the cosets of H. X plus H plus y plus H is equal to x plus y plus H. Below is the group table of the cosets. Okay, next, let G is equal to S3 consists of element E, alpha, alpha square, beta, beta alpha, and beta alpha square, and H is generated by alpha. The left cosets are EH consists of E, alpha, alpha square, and beta H has beta, beta alpha, and beta alpha square. The group table for S3 as shown as below. Next, if M1, M2 are in the same coset and N1, N2 are in the same coset, then M1 multiplied by N1 and M2 multiplied by N2 are in the same coset. We can define multiplication on the set of cosets as MH multiplied by NH is equal to MNH. The group table for set of cosets has shown as below. And that's all for our group. Thank you.